Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we'll be looking at GCSE chemistry, separating metals from metal oxides. Now, this is an important topic because this builds on the previous reactivity series video, and this topic contains some more reactions that where reactivity series is actually really important. So today we'll be covering the formation of how the metal ore can be formed, and also one of the two ways we can extract the ore, the metals from its original ore. So, without further ado, let's get started. So, first of all, let's understand the formation of metal ore. How does that happen? Well, what is metal ore in the first place? Metal ore usually is a metal oxide. It's a metal in a form that is not a pure metal. For example, it can be an oxide, it can be sulfate, it can be nitrate. Basically, the point is that metal ore is not a pure metal. And what we want to do is we want to get a pure metal, because metal ores usually are a powder of sort, and they don't have the properties of metals that we actually want. So we need to extract the metal from the ore. But before we get onto that, let's see how ores are formed. So ore can be formed in the sort of natural conditions. When the metal is in the earth, it is exposed to oxygen, and that oxygen reacts with the metal to make a metal oxide. In most cases, that would be the ore that we'll be looking at. So, for example, in here, we have an example reaction. We have two magnesium atoms reacting with oxygen to give us 2 MgO, 2 magnesium oxides. So that's the ore we get. Now, here I drew up sort of electron diagrams and to show you what is actually going on, because this will be important. I will explain later. So here we have 2 magnesiums, and here we have element of oxygen, which is 2 oxygen atoms joined together by a double covalent bond, which is why they share 2 pairs of electrons. Now, those 2 magnesium atoms, well, what they want to do is they want to either fill up their outer shell, or they want to lose all the electrons in the outer shell. So all of these guys can get together and they could come up to an arrangement where everybody is happy. Everybody has either full outer electron shell or empty outer electron shell. So this is what happens. Each of these magnesiums gives away 2 electrons to each of those oxygen atoms to form ionic bonds, because this is metal and non-metal, so they undergo ionic bonding. So as we can see here, magnesiums have no electrons left because they gave them both away to each respective oxygen atom, and then oxygen atom has now full outer shell of 8 electrons. So they are happy, magnesiums are happy, and that's the optimal arrangement, which is why that whole reaction happens in the first place. Now, what else has happened here? Well, what has happened here is magnesium given away 2 electrons. So magnesium has been oxidized because it has given away 2 electrons. Now, oxidation is where an atom or element or a molecule loses its electrons. So here magnesium was oxidized. So I'm going to write this down for you. Oxidation is equal to electron loss. Now, that is the correct definition of oxidation. Now, some of the older and less strict definitions sometimes claim that oxidation is gain of oxygen and reduction is a loss of oxygen. Those are older definitions, which sometimes are still used, because, of course, that is true. Magnesium gained here oxygen, therefore it got oxidized. But in a strictest sense of meaning, in the most correct definition of oxidation is electron loss. So magnesium was oxidized because it lost 2 electrons to each respective oxygen atom. So that's very important. So when we form a metal ore, we can say that a metal gets oxidized. Now, as you can imagine, extraction of metals from their ore, when we actually want to have a pure metal from a metal ore, extraction of metals is an example of reduction, because the exact opposite happens. The metal will gain electrons. So here we have an example. We have 2 iron-3 oxide molecules reacting with 3 carbon molecules, giving us 3 carbon atoms, giving us 4 iron atoms and 3 carbon dioxide molecules. Now, this is actually 1 out of 2 ways that we can extract a metal. We can extract a metal from its ore in a blast furnace. We can heat it up in a furnace in the presence of carbon, and that metal will, in some cases, react with that carbon to that metal oxide. That metal oxide will react with carbon to give us that metal that we wanted. Now, when will this work? Because there are 2 ways. One way is this in a furnace, and the other way to get the metal from its ore is electrolysis. And in some cases, we can only do this via electrolysis. But in some cases, we can do it using this furnace reaction. And that is all dependent on reactivity series. That goes back to our previous reactivity series video. Check it out, by the way, if you are not sure what reactivity series is. So here I'm prepared a part of reactivity series. That's not the full series. They're available in the previous video, but this is a part because this is what's important at the moment. Okay, so what do we have here? We have the most reactive is magnesium, followed by carbon, followed by zinc, followed by iron, followed by copper. Now, why is this important? Because this reaction can only occur. This can only occur in metals that are less reactive than carbon. And that's the importance here. So iron in this case works because it is less reactive than carbon. However, magnesium, like here, wouldn't work because magnesium is more reactive than carbon. And this is in a way a displacement reaction. You can think of it that way. Because what happens is iron is bound to oxygen. However, it turns out that carbon is better at losing its electrons than iron is. So what carbon does, it essentially sort of steals these oxygen atoms, and then it binds itself to oxygen, leaving iron alone, because it's better at better at forming positive ions, or in this case it's sort of covalent bonding. But anyway, so carbon's more reactive than iron, so it sort of steals those oxygen atoms. That's what you need to know. It basically steals those oxygen atoms, and therefore iron is left by itself, and that's how we manage to extract iron from its iron-3 oxide ore, by exploiting the reactivity series. However, of course, we need to do this in a furnace, in high temperatures, in presence of carbon, so that's a little bit harder than forming metal ores, which can be done in natural conditions. So, okay, so the final thing we need to cover is that here we have essentially reduction happening. So, if we look at iron oxide, that iron has given away its electrons to oxygen to bond with it ionically, to form this sort of molecule. However, what happens here is that carbon took away those oxygens, and therefore iron's left on its own. So that oxygen had to give back those electrons. it had to give back those electrons back to iron. So iron has gained electrons at the end of this reaction. Therefore, we can say that iron got reduced, because reduction in a strictest sense of meaning means electron gain. It can also mean oxygen loss, but in the best definition is that reduction is gain of electrons. So let me write that down here. Reduction is equal to electron gain. Gain. There we go. Okay, so the final thing that we need, the easy way to remember this is by, one sec, I will just move to the next page. There we go. The easy way to remember this is oil rig. Oil rig. And what does that stand for? Well, oxidation is loss and reduction is gain. So oxidation is loss of electrons and reduction is gain of electrons. Oil rig. That's the way to remember this. So this is it for today, guys. Thank you very much for watching my videos. I really appreciate when you guys watch these videos. I hope this video helped you immensely. If it did, give me a big thumbs up. If you want to stay up to date on daily math, science and biomedical science videos, hit that subscribe button below. Thank you again and see you next time.